In this class, we discussed about torsion of circular and non-circular shafts. What is the basic theory required to analyze torsion problems using theory of elasticity? So this torsion chapter you have studied in strength of materials in your B level. So to understand the concept of torsion, let us consider a rod or a bar like this, subjected to torsion, that is twisting moment at both the ends. So you can see I have applied torsion here like this. So due to that, so the effect of that will be this whatever AB length is there, the AB axis is there, that will be shifted. That will be shifted to AB dash with some angle. So this angle phi is nothing but your shear strain here. So shear strain is this angle. So which is nothing but tan phi, BB dash divided by AB, you can take it. So that represents the shear strain. So the effect of torsion is shear strain. That means development of shear stress. Then if I take the length of the member as L, then you will be seeing an angle of twist also in the cross section. So theta is the angle of twist in the cross section. Suppose if this is B, this goes to B dash here. This angle is called as theta. You can see the difference between phi and theta here. Phi, of course, we have to measure along the axis, whereas theta you have to measure in the cross section. So D is the diameter of the circular shaft and R is the radius. So in your SOM, you have learned that maximum shear stress occurs at the farther distance from the center. So farther distance is the circumference. So at the circumference you have the maximum shear stress that is going to develop due to torsion. The effect of torsion is the development of shear stress and shear strain. That is the meaning here. Now, tau is taken as the shear stress. And one more important material property we consider in torsion is the polar moment of inertia J. So which is nothing but J is nothing but the sum of moment of inertia about horizontal central axis and vertical central axis, which we call it as Ixx and Iyy. Sum of these two is nothing but your J, or sometimes it is also denoted as IP, polar moment of inertia, and T is the torque applied, G is the modulus of rigidity. So these are the units we have to follow in the theory of torsion, which I have already learned in your strength of materials. We have derived one important equation called pure torsion equation in this form in strength of materials. E by J is equal to tau max by R is equal to d theta by L. So this is the important pure torsion equation when a shaft is subjected to only torsion or twisting moment. This is the equation we can use. So here P is the twisting moment in Newton millimeter. J is the moment of polar moment of inertia in millimeter power 4. Tau max is the maximum shear stress that is going to develop at the periphery of the section in Newton per mm square or MPa. R is the radius of the shaft in millimeters. G is the modulus of rigidity or shear modulus in Newton per millimeter square. Theta is the angle of twist. Okay, of course, theta by L is called as the angle of twist per unit length. So this is expressed in degree or radian per meter or millimeter. That is the unit. And L is the length of the shaft. So this is the this is the units. These are the units you have to use for applying this equation. And one more equation we have learned, that is P is equal to 2.T by 60. That means when a body is subjected to torsion, power can be developed, and the amount of power that can be developed is given by this expression 2.T by 60, where N is the speed of the shaft in revolutions per minute (rpm), and P is the power developed in watts. So these are the units we have to follow. Already these things we have studied. So circular, in circular we have both solid circular and hollow circular shafts. So we have learned in strength of materials, so how to calculate all these power and shear stress, all those things. So in the case of circular and hollow circular sections, that we have learned. Now there are certain assumptions you have made while deriving this torsion equation. So the assumptions are listed like this: material is homogeneous and it obeys Hooke's law. That means it obeys Hooke's law means the stress is directly proportional to strain within elastic limits. That is the Hooke's law, and it is homogeneous. It has got the same physical properties in all the three directions, XYZ directions. Second assumption is plane sections remain plane even after application of torque. That means plane sections before applying torque and after applying torque, they remain plane only. That means there is no warping. We call it as no warping. So plane sections, there will not be any undulations in the plane sections even after applying the torque. That is second assumption. Third assumption, shear strain varies linearly with distance from the central axis. That means, as I already told, shear stress is maximum at the periphery, so and it is zero at the center. So as you move from the center like this, so the shear stress values will differ. It will increase, and it is zero at the center, maximum at the periphery. So at different distances, various distances, we will have different shear stress values. So it increases with increase in the value of cos. That is the meaning of this. Then angle of this per unit length, that is theta, is taken as constant. So these are the assumptions we are going to make if we are deriving this pure torsion equation. But in the case of non-circular sections, this is for circular sections and hollow circular sections. For non-circular sections, please note that the second and third assumptions do not hold. So second assumption means plane sections, they do not remain plane even after applying torque. And third assumption is shear strain is not maximum at the farthest distance. That is the meaning. So these are the examples for non-circular sections where torsion can be applied. So T section can be T section, it can be I section, it can be elliptical section. You can see in case of elliptical section, one axis is called as the major axis, 2A is the major axis distance, another axis is called as minor axis. So all these equation of ellipse you might have studied already in your mathematics. Then these types of sections, especially thin wall sections. So sometimes you may have to go for air foil type sections, thin wall sections. These are examples for thin wall sections. Of course, we have to analyze the problems on these types of non-circular sections here. So here, these thin wall sections, they are analyzed when they are subject to torsion. So to find the shear stresses, we are going to use one important theory called Torsion theory. Torsion theory, which I will be discussing in the next videos. Torsion theory. Using the Torsion theory, so you can always analyze the problems on torsion on thin wall sections. So in the case of these non-circular sections, this is what happens. So if you take, I have taken here a rectangular section. This is a rectangular section subjected to torque. So this is the along the length. So this is the axis. You can say this is the axis. If torque is applied like this along the axis, then there will be warping like this. So these cross sections, they don't remain plane even after applying the torque. So plane sections do not remain plane. So undulations will be there, curvature will be there. They will not be in plane. That means we say that. So what we can say here is, in the case of non-circular sections, these are the things we are going to observe. Shear stress is not constant at a given distance from the axis of rotation. That is, cross section warp due to out of plane deformation. So this type of deformation is called as out of plane deformation. For example, you have XY as the plane, out of plane means it will be in Z direction. So the deformation will take place in Z direction. So that effect is called as warping, which will not be there in the case of circular sections. That is the main difference between circular and non-circular sections when they are subject to torsion. Warping is not there in circular shafts, whereas warping you can observe in the case of non-circular shafts, whatever may be used, any of these types of sections. Maximum shear stress or strain are not at the farthest distance from the axis of rotation of section. That means in this case, maximum shear stress occurs at the farthest distance, that is at the highest value of radius from the center, whereas here in the non-circular sections, so the maximum shear stress will not be at the farthest distance from the center or from the axis of rotation of the section. That is another important thing. Then shear stress is zero at the corners. So at the corners means, so you can take this as the corners. These are the corners you can say. So shear stress value will be zero at the corners. So these are some of the observations you can make in the case of non-circular sections. So in the examination, they may ask you to differentiate the torsional behavior of circular and non-circular sections. So we have to write these things with some simple sketches and examples. Main important difference is warping. In the case of circular sections, warping is not there. In the case of non-circular sections, warping will be there. So non-circular sections, they are analyzed using this theory called Franz theory, whereas circular sections can be analyzed using this pure torsion equation. So next class, I will be telling you what are the fundamental equations governing torsion and how to develop some of the expressions for this torque or shear stress in the case of elliptical section or in the case of thin wall sections, all those things.